Conic sections. Algebra 2, we did a little bit with conic sections. That's what this cool cone here is illustrating. And when we take conic sections and we slice it different ways, then we get different shapes, a circle, an ellipse, etc. So that's why they're called conic sections. And if we look right over here, we can generate, if you will, these conic sections. There are two napes, upper nape cone, lower nape cone, an axis right in the middle, and then if you take another line and you just do a circle around, well, the circle around at the top with this point fixed at the vertex will make another circle around down here at the bottom, and it cuts out in space these two cones or these two napes, these right circular cones. So the conic sections that we might look at, and we're not going to look at all of these, we are going to look at an ellipse, and that's where, do we start with parabolas today? We start with parabolas today. We will get to an ellipse, and so that's just coming through one nape at an angle there, not perpendicular to the axis. It's going to be an ellipse. A parabola, we come through it where we go through that top part of it, we get a parabola from it. A hyperbola, when we slice through so that we catch both of these cones here, we get a hyperbola out of it. If we take an ellipse and we slide that plane down until it hits right at the vertex, you get a point. An ellipse, if you tilt the plane, becomes a circle. You slide it down to the vertex, becomes a point. Both circles and points are actually degenerate ellipses. They are a form of an ellipse that has just lost some of its characteristics, I guess we could say. If you take a parabola and rotate or slide that plane until it hits the edge of the vertex, it becomes a line with it. And a hyperbola, if you slide it in to hit the axis, it becomes two intersecting lines. So these bottom ones are actually special cases of these top conic sections. So they are degenerate conic sections. We don't study those degenerate ones, but just so that you're aware that that's what that means. When we have second degree equations in two variables, all of them make conic sections. And so a way of writing second degree equations in two variables, x and y. And you notice I can have x and y squared. They don't have to both be squared, but we can go all the way up to having both x and y squared. This right here is the standard form or general form of all conic sections. All of them can fit into this form right here. Now, if I'm going to have different kinds of conic sections, the A, B, C take on different values to them. We are actually not going to study the conic sections that have that xy term. Now it's there. Those are conic sections that have been rotated. We are just going to study ones that are either horizontal with the x-axis or vertical with the y-axis. But we can take them and we can rotate them through different angles. And some of that, a little bit of that is in the book. But that's what's going to happen. So our conic sections will not have the xy term, but they will have these other terms. Now, sometimes the value is 0, such as if this c right here is 0, I don't have a y squared term and I only have an x squared term, etc. But all of them can fit this form. A, B, and C cannot all be 0. If A, B, and C are all 0, it's no longer a conic section. It's a first degree equation. It's a line, is what happens with it. So starting with the parabola, some of the definitions of parts of a parabola we will start with and maybe add something. Parabola, the set of all points in a plane equidistant or the same distance from a line, that line is called the directrix, and a point, and that point is called the focus. So if we draw a line, it will be called the directrix, and if I choose any point, it will be the focus, and I find the set of points that are the same distance between those two things, the shape it forms is a parabola. So let's look right here. If I pick a point, the focus, and then I pick and just draw a line somewhere, it can be drawn anywhere, draw a line somewhere. This is the directrix right over here. And excuse me, and then I measured the distance between them. Well, if I measured the distance between them and took halfway, that is equidistant, that point is equidistant from the focus, equidistant to the line down here. And this is the vertex of my parabola. And then I picked any other location and measured the distance to the focus and the distance to that line and made sure it was equal. Then those would create a parabolic shape, a parabola, when we were done doing it. So the definition of a parabola in a plane, it's a two-dimensional shape. In a plane, it's the set of points that are equidistant from a point called the focus and a line called the directrix. That's how we can generate a parabola. Now, let's look at some letters or variables we are going to use with this. And we're going to start out looking at parabolas that open up or open down. And one thing that we have that is characteristic for a parabola is this distance between the focus and the vertex. We use the letter P to indicate that distance. And that distance is the same distance between the vertex and the directrix, but it's actually going in the opposite direction. It might have even have been better to call that negative P, just for the direction to it. It's the same distance P. So this value P, or this distance P, is going to be the key value that helps us write equations for parabolas. Now, when I have them opening up, the p-value is positive. When they open down like this one here, the p-value is going to be a negative value. Now, parabolas that open up or down are in this form. X squared equals 4py. Now, these parabolas have the vertex right at the origin. We're starting with the easiest parabolas. Stick the vertex right at the origin. So both of these have the same equation. X squared equals 4py, where p is that distance right over here between the vertex and the focus. So how do I know if it opens up and down again? It's if p is positive, then it's going to open up. Over here, the p-value is negative. It's going to open down. And something true about this 4p, since p is a number, 4 times p is a number, it's a value. That 4p is called the focal width of the parabola. It's the distance across the parabola through the focus. So that distance, 4p, goes all the way across. It gives us a nice set of points that help give us a rough sketch of where the parabola is going to go. So our standard form for a parabola looks like this. X squared equals 4py. Or y squared equals 4px. And the difference is, when y is the squared one, the parabola opens sideways, either right or left. So how can we remember? Well, one way to remember is if the x is the squared, the directrix is parallel to the x-axis. It's one way of remembering it. And if the y is the squared term, the directrix is parallel to the y-axis. There's different ways you can kind of set yourself up to remember which way it goes. So all parabolas whose vertex is at the origin, which is where we start, fit one of these two forms right over here. And that p-value is really the key. Now they give you a whole table here about what does the standard equation look like, which direction does it open, up or down, left or right, where is the focus located, and all sorts of little formulas. You can memorize the formulas if you want, but the whole key to it is just knowing the value p, and then I draw a picture. And then I get all the other things off the picture, off the diagram, real easy. You can memorize tables. I like pictures. Let's try it right here. Find an equation in standard form of a parabola who happens to have a directrix for the line x equals 2. So x equals 2, that'd be that vertical line right there. And whose focus is the point negative 2, 0. Negative 2, 0 happens to be the focus of it. Now, we have already learned that the basic parabolas that we're looking at have the vertex at the origin. Which direction does this parabola open, just from looking at that picture? Left. It opens to the left, because my vertex is going to be on my parabola, and the focus is going to be inside the parabola. I know it's something like that. I don't know the size yet, but I know it opens to the left. And so just from that, I know several things. I have a directrix parallel to the y-axis. It's in the form y squared equals 4px. I know it fits that form. And because I go left from the vertex to get to the focus, I know my p-value is a negative value. And that p distance, well, how far is it between the vertex and the focus? 2. That p distance is 2, and I know the p is a negative 2 because it's going to the left. If I was going to the right, it would be positive. Just like up is positive and down is negative. So I know what my p is. All I have to do is substitute that right there, and I've got my equation. Y squared equals 1 4 times negative 2. Now, if I was asked to really graph this, let me take my sketch away, I could use this 4p. Now, it's the absolute value, so the focal width is 8, and it's halfway each side, 4 to one side, 4 to the other side. So from this focus, 1, 2, 3, 4, I know it goes through that point. 1, 2, 3, 4, I know it goes through that point. So my sketch wasn't too bad, was it? You could get more points if you wanted to, but that's enough to get a kind of an idea of where that thing goes. Oh, it doesn't look much like a parabola. Use your imagination. That's a little better parabola than the other one. But you get the idea. So that focal width is good to give us a sketch of what's going on. The next thing we're going to do is move this vertex. Instead of having the vertex right at the origin, let's just move it. And we're going to use the letters H and K for where our vertex is. And it works like transformations of any equation. If I subtract a number on the x, it means I've moved it right that far. If I subtract a number on the k, it means I moved it down that far. So it's the backwards on that x. No, I shouldn't have said it that way. It's the opposite. I have moved it down that far. I moved it up that far. I moved it up that far. Here's what you do. When HK is the vertex, notice it is the opposite of H, the opposite of K. Let me put some numbers. So if my vertex is at 2, -3, my equation, I'll just say it's this first one, x minus 2 quantity squared equals 4p, I don't know what p is, y plus 3. Y plus 3. There'd be the equation. Just the opposite sign. And again, then they say all these things that you can memorize if you want, or I just use the diagram and figure them out. And the whole key again is that p distance. So let's try one of those. So they say here, find the standard form of equation of a parabola happens to have the vertex at 3, 4. 3, 4. So I know I have my vertex right here at 3, 4. And the focus is at 5, 4. Let me write this in a different spot. Focus is at 5, 4. So here's my vertex, which is 3, 4. And here's my focus, which is at 5, 4. Well, I already know, must be a parabola like that. And I know my p is what? P is a positive 2. The distance between the vertex and the focus is 2, and it's to the right. And because it's oriented this way, which equation? Is it the x squared or the y squared? It's the y squared one. So I know it's going to fit this form. Y minus k, the k goes with the y, quantity squared equals 4p times x minus h. I know it fits that form. So I can fill in a bunch of stuff. I know the vertex right over here. So I am going to say y minus 4, the y value, quantity squared, equals 4 times p. Well, p is 2. 4 times 2 is 8. 8 times x minus 3, the x value for the vertex. Standard form of the equation. There it is. If they ask us for other things, like where's the directrix? Well, if I went 2 to the right to get to the focus, I would go 2 to the left to get to the directrix. It would be the line x equals 1. We just figure it out from the graph where it would be. They didn't ask on this one. Use a function grapher. So we're going to use a calculator here in a minute to graph this parabola, as in example 3. Well, we already know what it kind of looks like. That vertex was at 3, 4, and it's a y squared, and that's a positive value, so I know it opens to the right. 3, 4, positive value, opens to the right. So we know we should get something like this. But if I am going to use a function grapher, functions have to pass the vertical line test. That's not a function. But if I cut it in half, the top half is a function by itself, and the bottom half is a function by itself.
Only goes through one.
What's that?
What's the vertical line test if it goes through it once?
Vertical line test, it can only go through it once to be a function. What we have here is for any x value, or for x values, we have 2 y values. Functions can't have that. Let's see how we can rearrange this equation to actually make it work into our calculators. Y minus 4 squared equals a times x minus 3. What we need to do is solve for y. So y equals is the idea I'm trying to get to. So if I'm going to solve for y, well, I could get rid of that square if I took plus or minus the square root. Y minus 4 would equal plus or minus the square root of a times x minus 3. And then just add 4. Y equals 4 plus or minus the square root of a parentheses x minus 3. Now really there are 2 equations here because of that plus or minus. And so on our calculators, and I've got to get mine started, do one graph with the plus part, and then do one graph with the minus part. And then we'll look at it. I put a link to Desmos there. Desmos can handle it directly. But a function grapher can't handle it directly. Bring it over here so you can turn off any plots if you had them on. I'm just going to do Zoom standard window. Notice any problem? Doesn't really connect. And it just is because of the resolution of the screen. Look in your book at this example number 4. Does it give a dimension on the window? Do they have a graph? I think they have a graph, don't they? They say -1.7 and -2.10. Let's try that. I'm going to hit the window. X negative, what was it? -1.7? So -1, x max to 7. And negative what?
2.
-2 to 10? -2 to 10? And let's hit graph. Let's see if it fills it in. There you go. So in other words, if you get the right dimensions, you can actually get it where it will show the thing up. So it's there. We can do it as on a function grapher if we just split it in half. But it automatically splits it in half when you do that plus or minus when you're trying to solve for y. All right, what did I do? Oh, there it is. Okay. Using standard forms with parabolas, prove that this graph or this equation actually is a parabola. Figure out what its vertex is, what its focus is, and what the equation of the directrix is. Well, that one kind of looks like the original form we had, that ax squared plus bxy, that stuff. Well, I know that if I have a parabola it's going to fall into that thing where I've got something squared, 4p, and then something over here. And looking at this one, I notice that the y appears to be the squared term on it. So what I'm going to do is isolate the y, complete the square, so we get a perfect square binomial that we can write. So we're going to take the y squared plus 2y, I'll leave some space to complete the square, equals, move the other stuff over, add 6, subtract 13, so 6x minus 13. Now I'm going to complete the square here. Remember what to do. Half of 2 is 1, 1 squared is 1. Add 1. Well, better add 1 on the other side, keep it balanced. Now on the left, I should have a perfect square trinomial. Y plus 1 quantity squared. Over here, I have 6x minus 12. Now I want that 4p, that number, factored out. I factor out 6. Y plus 1 quantity squared equals 6 times x minus 2. So there is the parabola in the form that we're used to. Can you tell me what p equals?
3 over 2.
Yeah, well, I do know this. I know that 4 times p equals 6, and so I can solve for p. 6 over 4, reduce it, 3 over 2. That's really the key to this whole thing. Let's start with the vertex. They wanted us to find the vertex. Well, I can read it right from my equation. 2, have to start with our x, negative 1. 2, negative 1. There's my vertex. Now I'm going to do a little graph at this point. 2, negative 1, my vertex is right over here at 2, negative 1. We are supposed to figure out where the focus is. But which direction does this parabola go? Look at that equation. It's to the right. It's a y squared. I know this thing is heading off to the right. It must look like this because my p is positive and it's a y squared one. So my focus, I know, must be right in here. And how far did we have to go to get to that focus?
3 over 2.
3 over 2. That 1.5 is going to get us to the focus. So if this vertex is at the point 2, negative 1, well, I just need to move to the right, which is the x value. Instead of going over 2, I'm at 3.5. 7 over 2. 3.5, negative 1.
7 over 2.
So my focus, 7 over 2, negative 1, or 3.5, negative 1. My directrix, well, I know my directrix is just back to the left. And I know it's back to the left 1.5, the same distance. So I am at what x value here? I'm at 1/2. I thought the vertex was at 2, and I backed up 1.5. I'm at 1/2. This is the line, x equals 1/2. It's a vertical line, so it's x equal. So my directrix, and we need to write the equation of a line, x equals 1/2. So there's all the other stuff they asked about. And like I say, a diagram to me is the easy way to do it. Instead of trying to memorize, okay, what's the little formula? I just look at the picture and see which way we need to go. If we take a parabola, so here's my parabola, and I rotate it through space, I would cut out this bowl shape. Or we call it a paraboloid of revolution. I have revolved that parabola around its axis right over here. So I get a three-dimensional shape. And paraboloids of revolution, for those in physics class, a focus, we just looked at mirrors, and a parabola perfectly focuses everything right on the focus point. So we can work two directions for it. A spotlight has a light at the focus. And when the light goes out in all directions from that light bulb or that filament, it reflects off the paraboloid walls and comes out exactly parallel to each other, so you have that beam of light. Now, some of you have had flashlights where you can rotate the flashlight and it makes it wider or narrower beam. What you are doing when you're rotating that flashlight is you're moving that light bulb in and out compared to that reflector, which should be a parabola, is what it is. And so as I move it in and out, it changes that beam. And when I have that light bulb right at the focal point, that beam is exactly parallel. So you get a parallel beam that's coming out. Headlights, they work the same way. The opposite is when you have satellite dishes. When you have satellite signals coming in, well, that signal is coming in parallel. All these beams are coming in parallel at you. And it reflects off the dish, and it all gets concentrated on that one point, the focus point. And that's where you have the receiver for your satellite dish. Now, old satellite dishes were in this shape, these big old huge things like this. Now, if you look at a DirecTV or Dish Network, something like that, it'll look a little bit different. You'll see something like that. I mean, here it's attached to the roof over here. And it looks a little more like this. Well, what they have done is instead of doing a symmetrical around the focus, they have just cut it off right here. They're just doing this part of it right here. It still reflects to the focus, but then they are able to stick the arm in, and then it connects right there. And so most of the modern ones are just that shape, but it's still a paraboloid. It's just a different section of it that they have cut out. I know my picture is real beautiful.
So, do you think the waves that don't come in parallel, they just don't?
It will only receive, it will only catch the waves that are coming in essentially parallel from that dish. Now, from that not from the dish, from the satellite. The satellite is really broadcasting it in all directions, or it's beaming it down like this.
So if it doesn't parallel.
So, yeah, you're not going to pick it up. The only ones you get are going to be the ones that are in that narrow band that are coming in essentially parallel. So any type of radio communication works with these paraboloids when you send it from one to another. Parabolic microphone. Football TV. On the sidelines, have you ever seen guys holding these big, and it might be at soccer too, stadiums, kind of like a clear glass, it's a plastic acrylic thing on the sideline? It's a parabolic microphone. That's a reflector. They're holding this thing, and there's a microphone that's situated right there at the focal point. And so they can aim it out there at the action going on at the field, and the faint sounds all get picked up and then concentrated into one point so you can hear it. So you want to hear what's happening inside somebody's bedroom as they are talking, or living room as they are talking? As they are talking, those windows are moving very, very faintly with the sound wave that is there. So if you can get something that can pick up that movement, like maybe you shine a laser at that and then concentrate it back, not trying to teach you how to spy or not, but this is what goes on. I mean, that's how they do it. They use technology like that. They can pick up very, very faint signals and then magnify them, and, oh, I know what's going on right there.
Like those little gun things that you point and kind of magnifies it and stuff.
Yeah. Yep.
Like with a cup on a wall, is that what it does? Or is it just echoing?
Like placing a cup against a wall, it's kind of the same thing. It's not a parabola. It's concentrating it, but it's not a parabola. So it's the same idea as you're trying to concentrate that energy to vibrate one thing that's bigger so you can pick it up. All right, what do we use? Parabolic reflector with a microphone at the reflector's focus to capture the conversation among the players on the field. It says the parabolic reflector is 3 feet across and 1 foot deep. So we are trying to get where the microphone is going to be placed, so we want to get the equation that matches it. So we do the easiest one possible. We put the vertex right at the origin. And if it's 3 feet across, well, I know I have 1.5 feet on each side because they're symmetrical. And the 1 foot deep is right there. There's the 1 foot deep. And so that's where they've come up with these 2 points on it. Over 1.5, up 1, back 1.5, up 1. So if I am going to write an equation, well, I've got a parabola that I drew going up. So it's the x squared one. And it's the simplest one, 4py, because we put the vertex right at the origin. I mean, if we're going to draw it, let's make it easy. So all I need to figure out is that p-value, because that tells me the distance to the focus, where the microphone should be. Well, this is an x and a y value. I should be able to substitute it in, and the only note is the p. So if x is 1.5, 1.5 quantity squared must equal 4p times y, which happens to be 1. 1.5 squared is 2.25 equals 4p, so divide by 4 for me. 0.5625. 0.5625 feet from that vertex point. That's where you should stick that microphone, and it'll be right at the focus. That's all they're saying there. And that's it for this first section. Pretty straightforward.